Welcome back to LGDinTECH Podcast. This is the place where we explore the intersection of advanced material and the next frontier of human innovation. I want to introduce a new term to you today, TGGD, which stands for Technology Grade Grown Diamond. So you're going to hear that a little bit in the podcast today, and you're going to hear it from us, and you're going to see it in writing from us. Today, we're moving to the atomic heart of quantum revolution. When people think of diamond, they think of luxury. But in the labs around the world, diamond is something entirely different. The world's most powerful semiconductors and ultimately the platform for quantum sensing. Joining us today is a visionary and center of this transformation, Dr. Fleming Bruckmaier, the CTO and co-founder of QuantumDiamonds. Born as a spin-off from the Technology University of Munich, QuantumDiamonds is doing what was once thought impossible, using perfectly imperfect lab-grown diamonds to make the invisible visible, detecting microscopic defects in AI chips and even tripling the detection rate of undersea sensors. This is all revolutionary, and it's happening right now very quickly. Fleming, thank you so much for joining us today.
Thanks for having me.
Can you just give us a little bit of background and maybe some overview of what's happening at QuantumDiamonds?
Yeah, sure. So the core of the technology, which is the reason why I'm here, is diamond-based. So we use defects in diamond called nitrogen vacancy centers to detect and measure mostly magnetic fields. And we apply this in the semiconductor industry where we're looking at magnetic fields produced by computer chips to localize failures and defects, helping the industry leaders like NVIDIA or Intel improve on their products, find defects in manufacturing, basically make more reliable products and producing the chips of the next generation. At the moment, we're launching the first tools here, and we're also looking forward to move towards inspection, which is then really in the production line itself, inspecting every die, every wafer manufactured for defects, ramp up the yield, ramp up or reduce the cost of each individual computer chip by introducing new metrology tools, which are always required, in particular when you're at the leading edge.
Fascinating. I didn't know about that whole inline. That's very exciting. People are talking about that now because it's so needed. Diamond is getting more incorporated. So it's definitely needed. Good for you guys. Hi, we have big news at LGDinTECH. In May, we're evolving to DimeTech.market, the world's first dedicated B2B marketplace for technology-grade grown diamond, TGGD. If you're building a future in semiconductors or quantum sensing or advanced optics, aerospace, this is your mission control. Buyers will be able to source high-quality diamond material, advanced growth and processing equipment, expert testing validation services. Sellers can connect with a global B2B audience for wafers or substrates, seeds, reactors, laser and polishing systems, and specialized lab services. Something brilliant is growing. To get early access, email me at liz@dimetech.market, and I'll give you the special code. So why don't you share with us just a glimpse of the short term, which maybe you just mentioned, but really what's the long-term goal for QuantumDiamonds?
Yeah, so in the short term, we're really focusing on failure analysis, which is more of a lab-based market. So you have a lab, and the typical metrology tools there are typically optical, thermal imaging, for example. So you have a chip and it heats up and you localize where it heats up. And we're now introducing this new technology, which main benefit is depth. So you can look deeper into stacks, and that's a trend that the semiconductor industry really is pursuing right now, using the third dimension as a dimension to scale the chips in. So that's something where we're launching the first tools now. One is actually going to the West Coast in the US. One is going Asia in the next weeks. Yeah, we're excited in the short and midterm how that's going to develop. And in parallel, as I just briefly mentioned, we are developing a tool for inline metrology, where the name of the game is throughput. So you really want to be quick. You want to measure quick, keep up with the other production machines, and you obviously need to be very reliable. So here we are in a demonstrator stage, and we hope to launch something in around 2028.
Oh, fantastic. So you're shipping all over the world now. That's really exciting.
It is. Also comes with a lot of new challenges, but we're managing.
I bet. Most people view diamonds as valuable because they're flawless. I mean, that's what the gem industry has taught us. However, in the quantum world, the value comes specifically because of the intentional defects in the NV centers. How important are these NV centers when it comes to quantum diamonds and your work?
Yeah, I mean, for us, they're incredibly important, but also about the flawlessness of jewel diamonds, right? There is something that's called fancy colored diamonds. So there's colored diamonds also for jewels, and the colors come from defects, right? So I think there's like Kimberley diamonds, which are pink. Nitrogen vacancy centers actually also make diamonds pink. And yes, they're intentional defects, but they also have to be placed in pretty much the most flawless diamonds that we can produce. So it's really actually crucial that the diamonds are something that we call electronic grade, very pure. Yes, and these defects are atomic scale. So that's really one nitrogen that's basically replacing a carbon atom, and then like one carbon atom that's missing. They're trapping electrons. Yeah, the pink color comes from them basically absorbing light and then emitting again the pink light that we see. And we can use this pink light, how much they basically emit back, can measure and make the amount of this light that they emit, we can make dependent on the magnetic field. So this is really an optical technique. It's a microscopy technique that we are developing. And one of the core IPs also that we have is that we have the process control of this diamond manufacturing. So we can really control the thickness of these nitrogen layers. We can control the amount of nitrogen in the diamonds. And this is really the core advantage of lab-grown diamonds versus natural ones, right?
Very true. Very true. Well, I mean, I think as someone who's been in the diamond material industry for a long time, the evolution of lab-grown diamonds has really made a lot of applications possible where natural diamonds never would. And it's interesting you brought up pink diamonds, because working with the largest pink diamond mining company for over 25 years, which came out of Australia, there were a lot of different colored diamonds, but pink was an unusual diamond, not just because of impurities that come from other elements seeping into the diamond as they're formed. But all of this was case study for the evolution of lab-grown diamond, which is really transforming and made a lot of what you're doing even possible.
Mm-hmm.
So when we see lab-grown diamond in the jewelry industry, we tend to separate the gem grade from the technology grade diamond. And that's really based on these impurities. So the TGGD, technology grade grown diamond material, enables quantum coherence in naturally or standard in lab-grown diamond. But that's just something that natural diamonds just can't match, as you mentioned. So have you tried any natural diamond application?
I don't think we've ever tried natural diamonds. I think there have been some publications using some, but I think also more for fun and not really as a serious application. I mean, you mentioned now technology grade diamonds. I think there's also different grades, right? So if you do diamond optics, you need certain optical grade diamonds that are pretty pure already. Manufacturers have their own terms. I think we typically try to go for electronic grade or ultra pure diamonds. And really, as I mentioned, I think you cannot have a good enough crystal. Every defect traps electrons. Every electron makes noise, and basically prohibits our measurements. So we are really looking for high quality crystalline material, and then again looking at how do you produce it. It's really a challenge. Do you go in grown diamonds in the sense of plasma grown diamonds, or you use high pressure, high temperature processes? Everything is pros and cons, and it's really challenging to improve on the material at a certain point. Yeah.
That's right. So far, I mean, we're still. I feel we're still in the infancy.
Oh, I mean, there's definitely ways of going forward, and we have to, for sure, there's ways to go. Yeah, I mean, material science hard. It's basically what I'm trying to say. It's a very challenging process, but then if you have an advantage, I think you have a decent moat.
So quantum computing, and quantum sensing often require, as they're building it out, it requires zero temperature ratings. Yet with Diamond, which is famous for being a thermal, for its thermal conductivity, how does grown diamond allow you to bring quantum applications out of that specialized, deep freeze type lab environment into real world environment, factories and medical clinics, etc.?
I can get technical here, but I think basically the simplifying it's what I said earlier. So like the noise, and also the reason why you want to cool down things is you want to prevent electrons to be around your quantum system. Electrons just interact with everything. Yeah, it makes it hard to control something that's as finicky as a quantum system. And Diamond, the quality that we're looking at is the electronic band gap of the diamond, meaning basically the fact that it is such a good electronic insulator, unless you dope it, makes for a very good insulation also for any type of electron that you can artificially trap in it. So that's really the reason why Diamond is so suitable for quantum technologies in the first place, and why you can also use it as at room temperatures. So it's definitely one of the core advantages, or the core advantage compared to other quantum technology platforms.
I mean, and the core advantage is so important, this particular advantage, because it just costs so much less to run something at room temperature as opposed to a highly temperature controlled environment. Much easier to build out, much easier to operate.
It's not only cost, I mean, and operation complications. It's an advantage in our measurement performance. Like, one thing that we want to do when we measure magnetic fields is we want to get close. And if we would have to have like a cryogenic system around it, it adds space, it adds distance, and then you cannot perform as well, and you might not even be able to add value really. So being at room temperature is a technological advantage, but it's also something that's enabling us compared to other also magnetic imaging technologies that require cryo.
Right. And the build out is so much quicker. So moving on a little bit, the conversation when Diamond, about 5 years ago, when technology grade grown diamond really started to get even more attention, people were, kept comparing it to silicon. So silicon defined the last 50 years of the tech industry. As we hit the thermal limits of traditional semiconductors, do you see technology grade grown diamond becoming the silicon of the quantum age? Where will we see the biggest impact first? Will it be in medical imaging or battery technology, perhaps just semiconductor manufacturing itself?
I don't want to bet on any quantum platform to build a quantum computer that quote unquote works first. So I really can't tell, but I think in sensing there's a lot of applications yet now. I think one core difference between sensing and computation is in sensing you do not compete with quantum, you compete with classical methods, right? I'm competing with when we do failure analysis, we compete with infrared imaging and other imaging techniques, optical techniques mostly. Our customer don't really care that it's quantum. They care that it works. I think biomedical, there's a lot of applications, but also still a lot of work to be done. Battery navigation, I think, is a big one. A lot of people putting their money towards GPS denied navigation right now in the security environment that we have at the moment. But I think in semi, it's the most prominent. Like, obviously, I'm a strong believer in the sensing use case that we are doing here at QuantumDiamonds. I think it's a useful thing for failure analysis. It's useful for inspection. But you also have the thermal conductivity that you've mentioned earlier, right? Diamond as a heat conductor, carrying away heat from computer chips. That is one of the core design problems right now in the semiconductor industry, to eke out performance percentages. And then you just have diamond as a semiconductor. You can use it to make high power semiconductors for various reasons that we have mentioned. They could perform much, much better than even novel materials that we have now, like gallium nitride or silicon carbide. It's a bet, I think, that a lot of people are taking as well at the moment. So these are really 3 use cases, and each of them can be transformative.
Very, very interesting. I think the big one of the biggest conversations we tend to have is that people are comparing silicon pricing to diamond pricing. How do you address that or try to overcome that? Or
diamond pricing is a big topic, and also like when we talk about sensors, you can go 2 ways. Either you make something like we do; it's a high-tech system that's highly performative, but also not cheap. And then the diamond plays, it's not insignificant, but it's a fraction of the cost of the total device. If you go to like a mass manufacturing, consumer electronics, maybe automotive, cost plays much bigger of a role. So I think in that area, lab-grown diamonds still have to get cheaper.
They have to get cheaper. And I think people within the supply chain, if they could see the benefit where diamond, basically normally doesn't wear out, doesn't break apart, you don't have to replace it as much. You don't have to turn everything off to go in and replace things. I mean, there's so many long-term advantages too. But getting cheaper is definitely, and it is getting cheaper.
It is. And a lot of people are working on it, right? First, they start with polycrystalline material, and then maybe heteroepitactical grown material that's, of a lesser quality. We couldn't use it, but it's definitely good enough, for example, as a heat conductor. And at some point, the quality will be good enough for us as well. So sadly, we need a high quality diamond. So we're the last ones to get it on large areas, but it'll happen.
Very true. Very true. Since we're talking about natural diamonds, which basically are, geographically concentrated, and lab-grown diamond supply chain is often opaque. How important do you believe the ability to grow this crucial material locally is to a company like yours? Do you think growers should be all over the world or centralized? How does that affect you guys when you're thinking about using this subcomponent part compared to other subcomponent parts you're using?
Yeah, I mean, supply chain is very critical for us. So we try to keep the nitrogen vacancy part in-house. So really, the last final steps we do ourselves. We also see it as core IP. On the substrate side, I think this is where we buy material as well. There is big name suppliers that exist. There's also smaller ones. Obviously, you probably are aware that there's a lot of suppliers in China and India. It's hard to pick out the ones that are good. We try to have a US, European, or Western supply chain in the diamond material, also just for, again, geopolitical reasons. Semiconductors are a strategic topic.
True. So is there anything else that you'd like to tell us about your innovation? What's coming up next? Anything we should be looking for? Any announcements you want to make?
I just want to emphasize again that I think the quantum sensing is it's quantum, but yeah, we really compete with normal sensing technologies and normal technologies in general. So I think we are called QuantumDiamonds, but we see ourselves as a semiconductor tooling company. We again, compete with existing technologies, and we're not like a quantum computing. We're not part of the quantum computing bet. So we're not part of the quantum computing race. Just like following up, also like the use case that we're targeting, I think the leading edge semiconductor nodes really are getting more complex and have also repeatedly required more sensing technology. So I think we really believe in developing the metrology and inspection tools for end of this decade, and then enabling fabs and next generation semiconductors as the one metrology supplier. So this is really the goal that we're aiming for. I'm excited where the road goes.
I'm excited too. One last question: when you're meeting or trying to meet new potential customers, do they know or understand or been exposed to diamond before? Do they just have a lot of questions about how diamond and technology is coming on the scene now?
I think mostly no. So, I mean, if they've been exposed to it, they've been exposed to it in the context of what we're doing. And then some of them are aware of it as a semiconductor material. But typically, the people that we're talking to, they're failure analysis. So they typically work with at least some somewhat established nodes. And diamond as a semiconductor material is still decently experimental. So yeah, I think it's not really common for our customers, but I hope it will become more common.
Me too.